Good morning, friends. Myself P.Kiran. I belong to ECE department. Today we are discussing about sampling process and sampling theorem. Coming to the sampling process, it is a very important process in the analog to digital conversion. If you take the analog to digital conversion process, it includes sampling, quantizing, and encoding. In the analog to digital conversion process, we have three blocks. One is sampling, another one is quantization, last one is encoding process. And coming to analog to digital conversion process, it is very useful recent days because every data is digitalized and storing in the systems as well as processing in the systems. Because of that reason, the analog to digital conversion process is very important process. In this, one of the process is sampling process. So coming to the sampling process, sampling, it is nothing but converting of analog signal to discrete signal. For example, let us consider analog signal and the discrete signal will be like this. So this is analog signal and this is discrete signal, and this is the signal before sampling and this is the signal which is after sampling, and this is the thing which is happening with the sampling process. Now, and how we are going to obtain the signal, discrete signal. So here consider analog signal and apply it to a product modulator, or you can say it as a multiplier, and for the another signal will be train of impulses and the output will be sample signal. So here in the sampling process, so we are taking a multiplier, and for that we are giving an analog signal as well as train of impulses, and the output will be equal to sample signal. If you see the analog as well as discrete signal, so in this the information is existing every instant of time. Coming to the sampled signal, the information is existing at particular intervals, that is at 0 instant, at TS instant, 2ETS instant, 3TS, and so on. Nothing but in the sampling process we are collecting the information at discrete time intervals. Nothing but at particular interval we are collecting the data. Now here we can say that we can define a parameter named as sampling frequency, and this sampling frequency value is equal to 1 divided by Ts. That is nothing but the interval at which you are collecting the data, and this is the thing of sampling process. Now, but why it is important? So just now I told that in every system we are storing the data in the digital form. So for storing the data in the digital form, we require the three blocks: sampling, quantizing, as well as encoding. For example, I would like to transfer the information from source to destination. So here, but I am having the data of analog in nature. So this analog signal I am not communicating to the receiver directly. The reason behind it is, if you transfer the analog signal directly to the receiver, the effect of noise is more on the process. If you convert this to digital and then the process to the receiver side, the effect of noise is less. Because of that reason, instead of transferring the information of analog directly, we are transferring the information in digital form. But a problem will come. That is, our required signal is we want to send the information analog to the receiver side, not digital. But we are sending the information, digital information to the receiver. So at the receiver side, we will be having digital information. But what we want to transmit, analog information, we will like to transmit. So for that purpose, from the digital, we need to reconstruct the analog information. So for that purpose, at the receiver side, the reverse of sampling process is required. That is nothing but from the samples, we need to reconstruct back our original information. That is nothing but analog signal. So in this, so if you want to reconstruct original information from the samples, we need to follow a theorem. That theorem we are calling it as sampling theorem. So what the sampling theorem is telling, we will discuss. What the sampling theorem is telling. So the sampling theorem is defined two ways based on the signals. One is different for different type of signals. One is baseband signals. Other one is band pass signals. So we will discuss the sampling theorem for baseband signals now. Now coming to the sampling theorem. A band limited signal, it is limited to frequency FM. Let us consider a band limited signal, and it is limited to a frequency FM. Then we can able to reconstruct back our original signal. From the samples if the sampling frequency is greater than or equal to twice of the highest frequency component. So that is nothing but just before what we have seen, sampling process. In the sampling process, we are converting analog to discrete. Now what we need to do at the receiver side, we need to apply the reverse process. Nothing but from the samples, we need to reconstruct our original information. So when we will reconstruct our original information, if you are following this condition, otherwise you are not able to reconstruct the original information. If you are unable to reconstruct the original information, then the process is not useful, right? So that's why we are following this condition. That is, the sampling frequency is greater than or equal to twice of the highest frequency component. Then we can able to reconstruct back our original information from its samples. And this is the thing which is informing by the sampling theorem. Now, in this, the Fs is equal to 2Fm is called as Nyquist the condition Fs is equal to 2Fm is called as Nyquist rate. Now you can get it out. In the sampling process, we are not transferring. In the sampling process, we are losing some information in the time domain. But even though you are losing the information in the time domain, you are able to reconstruct the original information if you are following this condition. How it is happening? So in the time domain, we are losing the information, but in the frequency domain, we are not losing the information. Because of that reason, we are able to reconstruct our original information from the samples. Right? So that we will see now. Just now we have seen the sampling process. We will have a multiplier. We will be having a multiplier, right? For the multiplier, we are applying the original information, that is analog signal we have discussed, analog signal x of t, and other signal train of impulses, and by applying this, by multiplying this, you are getting a sample signal. Just we can represent this with a single diagram, a simple diagram, original signal, and it is train of impulses, and the sample signal will be like this. This will be excess of t. Now, for proving the reconstruction process, we require a few things here. That is, this train of impulses. You can take it as 1 Ts, 2 Ts, 3 Ts like this. Now, this is the delta of t. Now, I would like to write the Fourier transform of delta of t. Delta of t is a train of impulse signal. The Fourier transform of this, I am assuming it as delta of omega. This is the time domain signal and this is the frequency domain signal. And the value of this delta of omega is equal to 1 divided by 2 pi summation n is equal to minus infinity to plus infinity, small correction, 2 pi n is equal to minus infinity to plus infinity delta of omega minus omega s. And this is the time domain signal and this is the frequency domain representation of this time domain signal. Now, how can we get it? Now, this x sample signal I can write mathematically as multiplication of x of t and train of impulses, delta of t. Now, if you apply the Fourier transform both sides, then the same signal is converted to frequency domain xs of omega. Now, it is equal to Fourier transform of x of t into delta of t. If two signals are multiplied in the atomic time domain, then those two signals are convolved in the frequency domain. That is 1 divided by 2 pi x of omega convolved with delta of omega. Just now we wrote the delta of omega as 1 divided by 2 pi x of omega convolved with 2 pi summation n is equal to minus infinity to plus infinity delta of omega minus omega s. Now here 2 pi is a constant, we can take it outside, so 1 by 2 pi is there, both are cancelled. Now convolution of a signal with train of impulse signal. So if you convolve a signal with impulse signal, you will get the same signal, and this is a property of impulse signal. So finally I can get it as summation n is equal to minus infinity to plus infinity x of omega convolved with delta of omega minus n omega s, and I can write it as summation n is equal to minus infinity to plus infinity x of omega minus n omega s. If you substitute the different values for n, then we can get it as x of omega plus x of omega minus omega s plus x of omega minus 2 omega s plus x of omega plus omega s, x of omega plus 2 omega s, and so on. And here xs of t, it is the time domain representation of x of t into del t of t, and the same information I am representing in the frequency domain, that is xs of omega, we are getting it as x of omega plus x of omega minus omega s plus x of omega plus omega s, x of omega plus plus 2 omega s minus 2 omega s, like that you will get the infinite components. Now this is the frequency domain representation and this is time domain representation. Now we will see how we are going to reconsider. Now I would like to draw graphically this information. So here first I am assuming that x of omega as like this, right? Now first condition I am taking as omega s is equal to 2 omega m. So case 1 I am taking as omega s is equal to 2 omega m. Now what happens? First, coming to the x's of omega, it is the addition of all these signals. First, what is there? X of omega. This is nothing but x of omega. Zero omega m minus omega m. And this is added with x of omega minus omega s. Omega minus omega is nothing but this signal is shifted to right side by the omega s amount. If it is shifted to right side by omega s amount, so what is the omega s value? 2 omega. Now 2 omega m plus minus omega, that will be omega m. 0 plus 2 omega m, that will be 2 omega m. 0 plus omega m plus 2 omega m, that will be 3 omega m. So then what you can get, and this is x of omega and this will be x of omega minus 2 omega m, that is omega minus omega s. Now same signal is there, omega plus omega s. So same amount, same signal is shifted left side. Like this. So if you plot x of omega plus 2 omega s, 4 omega s, then you will get the signals after this. Now if you see the spectrum of x's of s, it is repeating the spectrum of x of omega repeatedly. If you pass this to a low pass filter, with cutoff frequency will be equal to omega m, then it is going to allow the frequencies in between minus omega m and plus omega m. And the low pass filter is rejecting all other frequencies, nothing but from here to infinity, here to minus infinity, all are rejected. Then you are getting a spectrum like this, omega m minus omega m. So what happening, if you are getting this is nothing but you are getting x of omega. In the time domain you are getting x of t, that is nothing but original information. And that is nothing but if you are following the condition, that is omega s is equal to 2 omega m, then you can able to reconstruct your original message signal by simply passing the sample signal through a low pass filter. If you follow the condition omega s greater than 2 omega m, then what happens? From here, first signal will come, next signal will be shifted to some more extent. This signal will be shifted to some more left side. Then you can get the reconstruction very easy. If you are following the omega s is equal to 2 omega m, you require the ideal low pass filter. If you follow the condition omega s greater than 2 omega m, you require normal low pass filter. And so finally, we can able to reconstruct our original message signal if you are following the condition omega s is equal to 2 omega m or omega s greater than 2 omega m. So that is the thing, nothing but sampling theorem.